I apologize for the late start. We did have a bit of a couple of technical difficulties just trying to get started, and so that was cause for the slightly late start. But anyway, I think that everything's working good now, so I'm going to go ahead and get started, and I'll do a couple things here. I'm going to launch AFT Arrow. That way I can start my presentation, and while Arrow is starting, I can cover some slides here. So here's what we're going to do. What I like most about our software is that it's very user-friendly, easy to learn, and easy to teach it to other people. And so when you use our software, you'll be able to get a lot more done in less time. You're going to be able to avoid a lot more mistakes because of our standard formats for building models. It makes it a lot easier to explain to non-fluids experts what's going on. And then finally, you can get the right answers faster, and that makes everybody happy. And there's a lot of different things that you can do with each of our products. Sizing applications, very easy to size pumps, valves, pipes, heat exchangers, all sorts of different types of equipment. You can do system scale up where you can use a model to be able to figure out if a scale up from a pilot plant will work. You can easily understand how the flow demands and pressure changes throughout your system. With a design feasibility analysis, the software will tell you if your design will work or not. And so it's a very good way of being able to test out your designs to make sure they'll operate the way that they're expected. Operational variants, you can easily model a great multitude of cases within a single model file, and that's called our scenario manager. It's one of the most powerful features in our software, and I'm going to show you how to use that today. You can easily model system configuration changes, full-on heat transfer analysis. You can do transient analysis. You can easily account for leaks or scaling or fouling in the system. If you are pumping a viscous fluid like an AFT Fathom, you can allow your pump performance to be degraded for that. You can easily account for your energy consumption and quantify what that will be. You can make sure that you're staying within your code compliance. You can do full-on cost analysis with AFT Fathom and AFT Arrow. You can do water hammer analysis and handle slurries. So there's a lot of different things that you can achieve with our products. It'll definitely help you avoid having to deal with complicated and confusing spreadsheets that could potentially be error prone. It'll help you increase your modeling efficiency and flexibility. You can easily create your own custom fluids and components. So if there's something you need to model in our software, you can easily create your own data. There's a lot of ways to easily report your results to your clients. And this is our suite of products that we offer. And so we have AFT Fathom, AFT Arrow, and AFT Impulse. I'm going to focus on AFT Arrow today. It models compressible flow for gas piping systems. We also have Fathom, which models incompressible flow for liquid piping systems. And then AFT Impulse models water hammer for liquid piping systems. And I'm not going to spend any more time talking about what kind of products we have. I'm just going to show you where you can find more information about it on our website. And so if you went to aft.com, that's where you can find our website, which I imagine you all know how to find that because you made it to the webinar. And so if you go under products and click on that AFT software overview, this will be where you can find all of our different products that we offer. So I'll leave you to that, and you can learn about that more on your own time. I'm going to basically focus on jumping into the software here. So I've already started AFT Arrow. What do I do next? And so I've got a blank workspace of AFT Arrow on my screen. This is the system that I'm going to model. I have a piping system which is modeling a relief flow path I've got a methane process, an ethane process, and a propane process. This is a very unique example because it makes usage of the Chempack fluid database. And when you use Chempack with AFT Arrow, not only do you have access to over 600 very accurate thermophysical properties, they know where the saturation lines are. So if you're condensing with any of those gases, it'll warn you in the output. But ultimately, the really cool thing is wherever you have a mixture point right here of different gases coming together, AFT Arrow will calculate the mixture composition for you. So in this model, I'm assuming that the pressures in each process are so high, 200 psig, that is causing my relief valve to pop open. So I'm modeling a relief valve as just a standard open valve that's discharging into the atmosphere, and I want to figure out what's the relief flow and what's each of the discharge mixture fractions for the multi-component fluid for those hydrocarbons. In addition to that, there's a couple of assumptions that we're making here. The first assumption is that we're going to be assuming an adiabatic process, so all the pipes are going to be assumed to be perfectly insulated. The second thing that we're going to assume is that all elevations are at 0 feet, where in reality, the relief valve is actually at 120-foot elevation. And so due to budgetary constraints, the engineer didn't have time to look at higher temperatures, because the process could range from 300 degrees up to 700 degrees Fahrenheit. Also, they didn't have time to look at the higher elevation. So is it a valid assumption to neglect higher supply temperatures and actual relief elevation? And the way that we're going to quantify that is by using different scenarios. And that's going to help us answer our questions. All right. So let me go ahead and switch back over to AFT Arrow now. Here's my blank workspace where I will build the model of my system. And so this whole white area right here is our workspace, and that's a canvas where you can build a model of your system. These are all the different components that you can model for your system. And we use the general term junctions to for any of those components. You got regular valves, control valves, relief valves, heat exchangers, fans and compressors. There's some fittings that you can model, and you've got boundary conditions. You've got a tank boundary condition, assigned pressure where you know what the pressure is directly, or you can do an assigned flow junction. If you know what the flow rate is, you can model that as a known flow boundary. So each of those components are going to be what you use in order to build a model of your system. Now, when you don't know where to start, the thing to focus on is the red status light down here in the bottom right corner. Red means stop, green means go. And so if you click on that red status light, it's going to pull up a checklist of items that need to be completed before you can run your model. And so if you just start going through this checklist here, the first option is specify solution control. This is where you define the solution method and the tolerances that will dictate if you have a converged solution. Now, the default Arrow solution tolerances that are already predefined for you are very tight and robust, and they will solve about 90% of the cases. So you're not going to have to go in here and fiddle around with the solution methods very often. So that's why the first option is already checked off for you. The next thing is to specify system properties. This is where you define your fluid data, and there are 3 different types. There's AFT standard, ASME steam tables, and then Chempack. Our AFT standard fluid database contains various typical fluids. There's probably about 20 to 30 of them that you can work from in this list, and all you would need to do is simply select a fluid, add it to the model, pick your equation of state in your enthalpy model, and that's all you need to do. So this is the most simplified way of defining a fluid in AFT Arrow. If you want more accurate properties for steam, then you can use data from the ASME steam tables. And the nice thing about this is that it knows where the saturation lines are. So if your temperatures are below your saturation temperatures, Arrow will clearly warn you in the output, and then you'd be able to figure out how much insulation do you need in the areas where your steam is condensing in order to avoid that condensation. And that's what the ASME steam tables would be able to help you with. Finally, we have ChemPack here. And ChemPack for AFT Arrow contains about 600 different fluids that you can work with, and you simply just add them into the model, just like so. And when you add them into the model, you define what fluids are being used at the boundary conditions, and then they can mix together with ChemPack, and then ChemPack will calculate the mixture composition, and that's what we're going to do in our example here. Now, the other nice thing about ChemPack is that you can create a static mixture from the get-go. So if you click on Create New Mixture and Add, this is really neat because you can do a multi-component fluid. So maybe you've got 90% butane, and for whatever reason, you've got 10% amyl formate. And so when you specify this fluid mixture, AFT Arrow will be able to calculate the mixture properties for you. So that's a really powerful capability with ChemPack, is you can create mixtures in that fashion. Now here's what we're going to do for my model today. In my model, the 3 different gases that I'm dealing with are methane, ethane, and propane. And so I'm going to add those 3 fluids to the list. So when I go back into AFT Arrow, I can just do a search for methane, and then ethane, and then finally propane. And there it is. Perfect. So once I add the fluids to my model, I click OK, and I've got a green check mark. So now specifying my system properties are completed. The next thing to do is to define all pipes and junctions. In order to define pipes and junctions, there has to be pipes and junctions. So I'm going to lay out the model at this point, which you can turn on a grid. That way it makes it a little bit easier to build your system. So I'm going to do this. We've got methane, and then we have another tank for ethane. And if I already draw one, I can do Control D on my keyboard, and I can, it's essentially copy and paste in one. So that's a duplication. And then we have a elbow here, and then we have a T, and then we're going to do another T where the gases will mix together again. And then finally, we have our exit relief valve way up over here. After you build the model of your system, essentially it's a game of playing connect the dots. So if you double click your pipe drawing tool, you can draw as many pipes as you want. So I'm going to go basically from the center of one junction to the center of the next junction, just like so. And there we have it. So now my system is built, but I want to clean this up a little bit. So since my model is built now, I'm going to turn off the grid. I'm also going to make my text size larger so it's easier to see it. So there we go. Perfect. Now I'm going to drag my labels so they're not being covered up by any of the pipes. Then you can rotate the icons. The orientation of these icons makes no difference on the results at all, but we're engineers, we like things to look nice. So I'm going to rotate them so that they appear in line with the model. And then for this pipe, I'm going to do Control Y on my keyboard. I'm going to draw a graphical segment. That's what you call it. And it's really just a nice way of being able to create some right angles in the model. And this does not represent that you have an actual elbow at that location. If you want to model an elbow, you would either need to use a real elbow junction, or you would lump elbows into the pipe fittings and losses window in that specific pipe. So all we have there is just a right angle in order to make things look a little bit nicer. Next, I'm going to rotate my T here, and my model is fully, oh, one more thing, my valve, we rotate that, there we go. Okay, after you go through and you build your model and lay everything out, you might want to lock your pipes and junctions down to the workspace so you can't accidentally move them. So if you do Control A to select everything, hit the padlock button right here, and that'll lock everything down. So if I try to move anything, it's not going to let me. So that's a good little safety net that you could make use of there. All right. Now, in my system here, all my pipes are going to be steel pipe material, and the majority of them are 3 inches in diameter, except for 2 pipes. This pipe right here is 4 inches in diameter, and this pipe is 6 inches in diameter. And there's also some common lengths. These pipes right here are 50 feet long. These two are 25 feet long, and this is 150 feet. So there's some global editing opportunities available for helping you quickly define your model. So I'm going to start with the pipes first. Now, in order to define well, let me back up a little bit. If you click on Define All Pipes and Junctions, it's going to do 2 things for you. One is it's going to turn on the light bulb, and it's going to highlight any label for a junction or a pipe in red, meaning it's not fully defined. And so this is a very good visual indicator to be able to quickly spot which objects on the workspace might be missing some information. The next thing it does is it opens up our flyout window right here, and it's going to list all the undefined objects, all your undefined pipes, all your undefined junctions. If you click on any of these, it's going to actually tell you down here which information is missing. So let me erase all my drawings there. And so if I select a pipe, I need to specify length, inner diameter, and friction model. If I did a tank, I need elevation, pressure, a fluid, and the temperature. If I did a valve, I need elevation, pipe connections, loss value, etc. So this is a very good way of being able to quickly find in a model of maybe 1,000 pipes and junctions. If things are missing some information, this will help you find it quickly. So I'm going to start with my pipe. So if I open up a pipe here, you can simply double click on a pipe or a junction, or you can select it and hit enter, and that'll pull up the pipe property window. Wherever you see blue highlighting, that indicates required input. So you need a length, an inner diameter, and a friction model, and that's all you need in order to fully define a pipe. Now, we do have several pipe materials built in for you that you can work with. So if your pipes were if your pipes were steel, you can simply select the material and then choose the appropriate size that you want and schedule from these drop-down menus. So that'll save you a lot of time rather than just entering the inner diameter directly. The next thing is if you click on user specified for the friction model, you have access to a lot more friction models like hydraulically smooth, expressive friction factor. There's a couple of correlations, either the Weymouth or panhandle correlations that you can use. Those are more simplified methods, and those are all available for your friction models. One key difference between AFT Fathom and AFT Arrow is that AFT Arrow is always doing heat transfer, no matter what. So by default, all of your pipes are going to be assumed to be adiabatic, perfectly insulated. If they're not, then make sure you go back and choose the appropriate heat transfer model that they should be. So if they're doing pipe convection, then you can enter an ambient temperature. You've got your internal fluid correlation, either Nolinsky or Dennis-Bolter. You've got conduction to the pipe wall, and then convection to the ambient conditions. And if you want to add layers of insulation, you can add up to 3 layers of external or 3 layers of internal insulation, or a combination of both. and that's where you'd specify your connectivity and your thickness. You can also choose from one of our pre-built insulation database sets. Now, in my model, I'm going to do some global editing here. All pipes are steel pipe. So I'm going to go to Edit, and then Global Pipe Edit, and I'm going to select all pipes, and I'm going to make them all steel pipe material. So I'm going to choose steel, and even though some of them are not 3 inches in diameter, I'm still going to set all of them to 3 inches in diameter. I'm going to go back and change the other 2 pipes that are not 3 inches one at a time. Now, here's the thing. It's asking me to input a length right here. Because it's blue highlighting, it means it's required input. However, if I'm doing a global pipe editing operation, that means that the pipe property window that shows up here is a template window. So when you're doing global editing, you only need to edit what you actually care about editing. So in this case, I don't care about the length. I only care about defining this information right here. That's all that I am concerned with defining at this time. So when I click OK, it brings up a list of parameters that I can change, and I'm going to do all of them just like that. Now, I'm going to go back in, and I'm going to do the lengths, and so pipes 1, 3, and 5 are going to be 50 feet long. And so I'm going to click on Select Pipe Data, type in 50 feet. You can change your units with the drop-down menu there. And I'm only going to select length at this time because the diameters are already defined. So with great power comes great responsibility. Global editing is very useful and very helpful. Just make sure you pay close attention to what you're doing. That way you don't accidentally change something that you didn't want to change. Next, pipes 2 and 4 are going to be 25 feet long. So I go in here and type in 25 feet and click length, and there we go. Now, just a couple other things. This pipe right here is 4 inches in diameter, so I'm going to change the diameter here to 4 inches. And then my relief piping is going to be 6 inches in diameter. And it's going to be 150 feet long. Perfect. All my pipes are now fully defined. Now I'm going to do the junctions. So my boundary conditions here, my process tanks, these are going to be at a 0-foot elevation, and then I'm going to define a fluid. So this tank is going to be methane. You could call it methane process for a name, and then you put in a pressure and temperature. So this is 200 psig, and the lower temperature is 300 degrees Fahrenheit. And click OK. Now that's fully defined. The next one here is going to be my ethane process. And I've got ethane chosen for my fluid. And it's going to be 200 psig and 300 degrees Fahrenheit. And then last but not least, I have my third tank. This is going to be my propane process. I'm going to choose propane from the drop-down menu. 200 psig. Units kill. So make sure when you're defining your units, or if you're working through any of our examples, pay very close attention to the units that you're using and the units that are displayed in the results and the units the answers are actually being given in. So just watch your units very carefully there. Awesome. Just a few more things to define, and then we can run our model. This elbow right here is going to be a standard elbow, so the loss factor is picked up from the upstream and downstream pipes from the appropriate loss model. Both of these T's, I'm going to keep things simple today, and I'm going to define simple T's, which means no loss. So you can account for losses if you want to. You would have to, if you do that, you have to make sure that this picture is defined exactly correct, and that you choose the correct branch pipe. So if you're going to do detailed T modeling, make sure you define that correctly. A tip that I would recommend is before you go in and start trying to account for all the losses in your T's is use simple T's first. The reason for that is because it's going to make simplify the calculations when you still have a high level of accuracy. And the important thing is you'll then know what your actual flow distribution is throughout your piping network. So if you actually have reverse flow in any of the pipes, the model will tell you, and that way you can make sure that you define your T's correctly. So be very careful in how you define them. The loss models for T's were developed by Idlechick, and they were developed under incompressible flow conditions. So they may not always be directly applicable to compressible flow applications. So just be very careful on how you use them. Make sure you define the orientations properly. That's all I'm going to say about detailed T's right now. That's a whole separate hour-long discussion in itself. Last but not least, our relief valve. So I'm going to call this relief valve right here. Now, initially, I'm assuming that the relief valve is at 0 feet because the engineer didn't have time to use the real elevation. And so here, the way that I'm going to model this is I'm going to specify a K factor of 0. The reason why is because I suspect that the gas velocity is going to be so high at that valve that it's going to sonically choke through that restriction. So I'm not going to have a subsonic loss in that case. I'm going to define a CDA value, which is an effective flow area, like the think of the vena contracta effect. And so that's my flow area. And this is going to help establish what's the pressure loss across the shock wave if I am in fact sonically choked. And I'm going to use the exit valve option, which means that I'm discharging right into the atmosphere. So when you do that, you specify 0 psig, and then the ambient conditions, the temperature can be, let's say 70 degrees Fahrenheit. So there's my relief valve. Now, as you can see, I have all 3 green check marks and a green status light. I could run my model and get my results. But before you do that, one thing that you want to do is take a look at the model data window. The model data window is an excellent tabular format for all of your input information. And so this is really good for going in here and scanning down the list of data, because you want to make sure you've got unit consistencies, that your values are correct, that you're not off by huge orders of magnitude and things like that. And I use the model data window for troubleshooting people's models all the time. And it's very, very helpful to quickly spot something that is not defined the way that it should be. That way you can then go back and fix it and then run your model and get results. So that's the model data window. Okay, I'm going to run my model here. Before you run the model, it's going to make you save, which is always a good thing to do. So I'm going to call this relief flow system. And thankfully, the model solves pretty quickly. Just takes a few seconds there, and we can take a look at the results. So let's break this down. There are 3 sections of results in the output window. We have our general section on the top, we have a pipe results section in the middle, and then a junctions results section at the bottom. Now, here's how things break down. At the top, we have in the general section warnings tab. So if you have any warnings or caution messages like this one, it'll tell you. And so that'll help you figure out if there's something wrong with your model, perhaps. Next is on the sonic choking tab. This tells you where you are sonically choked throughout your system. And as I suspected, I thought I was going to be sonically choked at the valve, which is J7, and I am. So that means that my restriction is causing a sonic shock wave across that relief valve. So a sonic choking tab, it doesn't mean that you have anything wrong in your model. That's not what it means. It's just, this is telling you where you've got sonic choking at. Arrow handles sonic choking very well. And then you've got a valve summary tab and a tank summary tab. Now, if you look carefully, we have two junction sections for results. We've got our junction summary tabs at the top, and then we have junction results here at the bottom. Here's how these two sections are different. The junction results at the bottom are common result parameters that are applicable to all junctions. So it's mass flow rate, pressure on the inlet, or inlet or outlet pressure, inlet or outlet temperature, enthalpy, density, loss factor. Those parameters are common to all junction types. However, let's say that you want to look at a valve CV. Well, the thing about a valve CV is that a valve CV means nothing for a tank. So if you want to look for a valve CV, you're not going to look down here. You're going to look up here in the summary tabs. So the summary tabs in the general section, these are output parameters that are specific to those types of components. So these are, my CV is going to be displayed in that summary tab right there. Now, I would recommend that when you are evaluating your results, the best way to do it is to focus on the results in the pipes themselves, because there's not going to be any ambiguity. You're going to know exactly what the pressure is at the inlet or the outlet, or the flow rate or the temperature, etc. Now, a couple of things about the pipe results is in Arrow, you have an axial points tab. So in order to handle compressible flow properly, we break each pipe up into individual segments. And so as we march along the pipe, we're solving mass balance, momentum balance, energy balance, etc. at each individual pipe station. And so this allows you to track what the results are at each pipe station along the pipe. So this is station 0, that's the inlet, station 1, 2, 3, etc. And these are the results at each pipe station there. The reason why this is important is because in compressible flow, your temperature profiles, pressure profiles, densities, your enthalpies, velocities, they're going to be non-linear. And so it's not as simple as inlet and outlet anymore. You've got a lot of stuff going on inside the pipe. So with that, let me show you what the profile path is. Erase my drawings here. So what I'm going to do is I'm going to generate a graph for my some values along that flow path here. So I'm going to go to my graph results window, and I'm going to hide my checklist now. And so I'm going to look at pressure, and I'm going to look at temperature, and I'm going to look at velocity. All right, so this shows you how your pressure, temperature, and velocity changes throughout your system. And as you can see, there are some areas of nonlinearity. And this is why the axial points are important, is to get enough resolution to properly handle the compressible flow. So I'm going to file this graph away for later. I'm going to call it P, T, V versus L. The reason why I want to save it for later is because when I go back and make changes to my model, I don't want to have to reset these parameters every time. All I would need to do is just double click on that graph. That's going to reload it right away. Lastly, my visual report is where I can graphically show the results right on top of the model itself. So I can show mass flow rate, velocity, let's show pressure, we'll show loss factor for the junctions. There it is. And I'm going to modify my display a little bit. make my text size larger. I'm going to do a color map. So I want to color code the pipes by the temperature change that they are. And so let's take a look at temperature loss. So what I want to do is I want to color code the pipes by the amount of temperature loss that they have. And so this is going to change the colors of the pipes. That'll tell me how many degrees I'm losing roughly in each pipe. And there we go. So I've got my results displayed right on top of the model itself. And so this is a fantastic way of being able to report your results to your clients or your colleagues. Makes it very easy for them to follow along what's going on in the model. So that's our visual report. And let me save that. Okay, so what is the answer to the questions? The questions are, what's the relief flow rate? Well, the mass flow rate is 38 pounds per second. So that's the relief capacity for your relief system. The other question is, what's the compositions of the gas? And so in this particular stream, it's only methane. This is only ethane. This is only propane. So in this pipe, we have a methane-ethane mixture. And then in this pipe, we have a methane-ethane-propane mixture. Let's see what those compositions are. The best way to figure out what the compositions are is to look at the output window, and you can go to the composition tab. And so the composition tab, it's going to break down what the flow rates are on a component by component basis. So in pipe 6, that's the important pipe that we're concerned with, because this is the one that has all three gases in it. So as you can see, your total flow rate is 38 pounds per second. A little bit of it is methane. The most of it is propane, and then you have ethane in the middle. So you can see what the actual flow rates are. If you go to the pipes tab, you can go to the output control and add concentration, mass fraction, or mole fraction. And I'm going to move these all the way up to the top here. There we go. Perfect. So that's how you can customize your output, is with the output window. So now when I look at the concentrations here, this is the concentration on a mass fraction basis. So as you can see in the final pipe, we've got 19% methane, 33% ethane, and 47% propane. So this way you can go and take that information to the environmental people. That way they can see what's going to be discharged in the atmosphere in a relief event. All right, so that's the answers to those questions. Let's take a look and see what's going on when you actually account for higher temperatures and higher velocities properly. So in order to do that, I'm going to do a scenario. So I'm going to click on my base scenario and create a new child. I'm going to call it higher supply temperatures. In this scenario, the temperature of each of these processes are going to be 700 degrees Fahrenheit. So I'm going to do a quick global junction editing operation. And that way I can edit the temperature at the same time. So 700 degrees. I'm only going to check the box for temperature. And that way I only have to make the change once. Now I can rerun my model. And based upon the higher temperatures, I'll see what the results are. Now, the really cool thing with the scenario manager is it allows you to also compare results from one scenario to another in the output. So I can go to my multi-scenario tab. I'm going to display the results of both scenarios side by side with each other. And so here I can see my results where when I account for higher supply temperatures, my relief flow rates are actually a lot less. So my final relief pipe is only 30 pounds per second for a higher temperature case versus 37 pounds per second in a low temperature case. So that's how you can easily see your results. You can also go back to the visual report and then show them, and that'll display them right here. And then if we want to go to the graph results window, we can regenerate our graph really nice and quickly. And you can see how the results have changed when you account for higher temperatures there. Next scenario is we're going to account for a higher elevation. So I'm going to create another child scenario, and I'm going to call it actual relief, if I can spell it properly, elevation. Now, when I make this identical copy, I've already changed the temperature in my previous scenario, so that's going to pick up the 700 degrees for my higher elevation case. So now my relief valve is at 120 feet. Rerun my model. Let's go straight to the visual report and see what the results are. So as you can see, when you account for a higher elevation, the results don't really change for flow rate. You're still getting 30 pounds per second when you're assuming a higher inlet temperature of 700 degrees Fahrenheit. You can also look at your results on the output window, and the nice thing is that we'll automatically color code the scenarios for you. And then you can also see, do you have different concentrations? Well, not really. You're getting right around the same concentrations in each of the different cases. So that doesn't change, but the flow rate changes a little bit when you account for different temperatures. But the flow rate doesn't change that much with neglecting the higher elevation. So that doesn't make a big deal in the results there. So that's a good example that gives you a nice little overview of the interface and how it works together and all of the primary windows. Each of these primary window tabs supports docking. So if you want to look at results and your model at the same time, you can dock it below perhaps, and maybe look at the heat transfer tab, and you can look at your model all at the same time. So you can dock windows either side to side or top to bottom. Also, they support dual monitor usage. So if you want to pull a window off and do its own separate screen, you can certainly do that. And so that's a really nice feature, is the dual monitor usage there. All right, let me come back to some slides here real quick. So overall, what is so special about compressible flow? Well, some key things here is that your velocity changes in a pipe. Your density changes in a pipe. They're no longer constant. And so that's what causes a lot of complexity of compressible flow. And your velocity changes are nonlinear. And you have also your density dependencies on temperature and pressure for compressible flow. So you're going to have to account for an energy balance and an equation of state. You can have sonic choking in your system, and accelerating flow is limited to your sonic speed at a Mach number of 1. And you can have multiple choke points in a system. You can have sonic choking in expansions where you're going from a smaller diameter to a larger diameter. You can have sonic choking through a restriction like a valve or an orifice, or if you're just discharging into a very large tank or the atmosphere, you can have sonic choking at the outlet of a pipe itself. And that's going to impact the behavior of your system, to where if you try to lower the downstream pressure, you're not going to be able to get any additional flow with that. So those are the things that make compressible flow very difficult to deal with, and it's very difficult to apply them to networks. So there are some ways that compressible flow has been handled traditionally. One way is to use incompressible flow methods, and those are just very inaccurate. They don't model real gases or heat transfer. They don't address sonic choking in any way. So really, whenever you're dealing with a gas system, you don't want to deal with doing incompressible flow methods. They're just not going to give you the right results. There's some compressible flow correlations out there. There's the so-called isothermal equation in Crane. There's a Weymouth method and the Panhandle method. They're just correlations. They don't handle real gas or thermal effects. You can only deal with them on a pipe-by-pipe basis. You can't apply those methods to a network. They don't even account for sonic choking. So here's what Arrow does. Arrow is going to solve these 5 fundamental thermodynamic equations simultaneously. So here, as you can see, your mass balance is now a lot more complicated. So it's solving the mass balance, momentum balance, energy balance, equation of state, and Mach number. And in order to get the correct results, when you're doing a compressible flow analysis, you need to handle all of these thermodynamic equations properly, and AFT Arrow does. And so it's going to solve all of these pipes in all these equations in every single pipe throughout the system, and then every junction we're going to balance mass, we're going to balance energy. In the example I showed you where you're using Chempack to calculate a mixture composition, we'll also balance the species in that case. So those are all the important fundamental thermodynamic equations that you need to pay attention to in order to handle compressible flow properly. All right. Let's touch a little bit more on sonic choking today. Again, your flow rate is going to be limited to sonic flow at a Mach number of 1. AFT Arrow does not model supersonic flow. In order to get supersonic flow, you need to have a very special geometry that is more of a converging, diverging nozzle. And that's for very special applications, and it's rarely asked for. So Arrow does not model supersonic flow. Again, you can sonically choke at a restriction, at an expansion, or an endpoint of a system. So let me pull up a simple example with an orifice plate. Erase my drawing here. Okay, go to my folder. Let's see. Just need to find the model real quick. There it is. Okay, so here we have an orifice plate in a system. And with the orifice, we've got a K factor equal to 10, and then our orifice area is 3 square inches. So your piping system is 2 inches in diameter itself. Your orifice area is obviously smaller. And there are 3 scenarios. The first scenario is we don't enter any CDA value for the orifice. So we're not specifying a flow area because we're going to assume that it's not sonically choking there. We're going to run the model first, and we're going to calculate a parameter called the sonic area. And the sonic area is a very useful output parameter because it helps you determine the margin in which you would be sonically choked. You have 2 additional scenarios where you're going to assume a orifice that is 20% higher than the sonic area, and then a scenario where it's 20% lower than the sonic area, and we're going to see where it chokes. Now, a quick note on sonic areas. As I mentioned, the sonic area is a very useful output parameter that is calculated in the results. And for the sonic area, you can compare what your effective flow area is, or your CDA value, in order to determine if you're choking or not. So here's a little picture that I drew several years ago. This was a very large, oversized orifice, if you will. So it's a pretend it's a very extremely thick orifice. The red line here that you see, the red boundary, that's our flow area. It's your vena contracta, it's the CDA value, and this is exactly what you're specifying. If your sonic area is larger than your flow area, then you're going to be sonically choked. Yes. However, if your flow area is larger than your sonic area in here, you're not going to be sonically choked. So if you make your orifice area really small, or if you make your orifice area really large, you're not going to be choked. So this is a blog article that I wrote a few years ago. You can find it on our website. So this will be demonstrated with this example here. So this example is already built for you. I'm not going to go through and define everything. As you can see here, our original scenario, we've got a K factor. The area of the orifice is 3 inches square, and K factor is equal to 10. And so with no CDA, we're going to see we're sonically choked. So I run the model here. I can look at the sonic choking tab. I do have sonic choking, but it's not at the orifice. The sonic choking is happening right here as you're discharging into the very large tank. And so you don't have any sonic choking there. So your orifice, no sonic choking. Now, if we go back to the results here, we can go to the orifice and scroll over to the right. Our sonic area is 1.37 inches square. So if you make a CDA value or an effective flow area that's larger than this sonic area, you're not going to be sonically choked. So you're going to see that here. If I go to my scenario, here's my orifice. So there's where I've specified a larger flow area than the sonic area. We're not going to have any sonic choking. So we run our model. No sonic choking again at the orifice. These results are exactly the same as the previous scenario. Now, let's look at the scenario where we make a flow area which is smaller than the sonic area. In this case, we will be sonically choked. So when I run my model here, you can see in the sonic choking tab, you are now choking at the orifice as well as the outlet. And if you notice, the flow rates are smaller. If I display the results side by side with each other, you can see that very clearly. So when you are sonically choked at the orifice plate, because you have a smaller flow area than the sonic area, your overall system flow rate is going to be smaller. And so that's a little bit of an overview on sonic choking. Now with that, that's basically all the time that I have today. I want to point out that we have tons and tons of incredibly useful learning opportunities that are available to you. So let me give you a quick tour to where you can find all those pieces of information. On our website, if you go to AFT.com, under the Learning Center, you can find information on our training seminars. We host excellent training seminars at our facility in Colorado Springs about 3 times a year, and these are the posted dates for 2018. And you can find the pricing down here below. If you have a bunch of engineers that you want trained, we can come and teach a seminar at your facility. For that, let me know if you're interested, and I can provide you a custom quote for that. So if you want to come to one of our seminars, register directly on our website. I recommend spending maybe a couple extra days out here in Colorado Springs because it's gorgeous and there's a lot of really cool things to see and do in a very short proximity to each other. So you'll definitely want to go around and see the sites. We've got tons of case studies on our website, technical papers. If you go to technical papers and find the article, Gas Flow Calculations Don't Choke, This will give you a much, much better understanding of how to properly handle compressible flow. So this is an excellent paper that you should read at some point after today's webinar. We've got tons of tips and tricks articles that we've written over the years, and these typically come from common technical support questions that we get. There are also tips on how to use the software more effectively and efficiently. And then we've got video tutorials, and finally we have our upcoming webinars and our webinar library. And so our webinars allow you to learn all sorts of different pieces of information. So we have all of our webinars scheduled throughout the year, so register for these and you'll be able to come and learn about some really exciting information there. Within the software itself, if you go to the help menu, you can access our main help file. Our quick start guide is available as a PDF. If you're a brand new user, the PDF quick start guide is the very first thing that you're going to want to walk through. This will get you very familiar with the basics of the software, and that's really important to go through. If you want more help and more tutorials, go to show examples under the help menu and then access your favorite units. And this is where you can find several additional walkthrough tutorials that will teach you additional features about how to use the software, like how to do cost calculations in AFT Arrow. So there's a lot of information that's available for you there. Okay, so other than that, that's basically all that I have for today. Thank you all very much for your time. Again, my name is Ben Keyser, and if you want, you can email me directly at benkeyser@aft.com, KEISER@aft.com. If you have any technical support questions, email those to support@aft.com. And for any sales-related questions, you can email those to sales@aft.com, or you can send them over to me as well. So that completes our webinar. I did record it, and so you will receive an email either later today or next week sometime, and that will contain a link to where you can watch the recorded version. So you don't need to email me to ask for the recorded version of the webinar. You will get it either later today or next week. So just hang on tight for that. Thank you all very much, and I hope that you have a wonderful rest of your day, and we'll see you in a couple of weeks when we're doing our next webinar. Essentially, we're doing our webinars every first and third Wednesday of every month this year in 2018. The only time is if there's a holiday during that week. And so first and third Wednesdays is typically when we're going to be doing our webinars. Thank you, everyone. Take care and have a wonderful day.